Okay, what we're looking at here is an application of calculus because we are asked to find a maximum volume of something. So we've got a piece of metal. Side length is 2 meters and 4 squares are cut out, shown in the diagram. It's going to end up with a height of x. So if we think about this as a sheet of metal, we cut off these 4 bits. Then what's going to happen is that this, and this folds upwards. So this is the base. These are all now lined up to here, and they're all facing up. They have a height of x. And therefore, this distance, this distance, this distance, this distance, this one are all x. If we're starting off with something 2 meters in length, or a side length that has 2 meters, and we're cutting something out, that tells us that the overall length here is 2 meters. So we're going to put that in. So I know this is 2 meters, which goes from here over to here. And I know that this is x. This is also x. Okay, now that I've got that, I can start doing some calculations. Now, for me to find the volume, I know I've got a box. It's length times width times height. So I know that so if this is, and now just one other thing to check, if this overall length is 2 meters, so from here to here is 2 meters, and I've cut off x here, I've cut off x here, that means that this part here will be 2 minus 2x. So I'll put that in here, 2 minus 2x. So now, we've got a width of 2 minus 2x, we've got a length of 2 minus 2x, and we've got a height of x. So that's what we're going to do, we're going to substitute that in. So volume equals 2 minus 2x times 2 minus 2x times x. We expand that, and we end up with, let's try to find my notes, 4 minus 4x minus 4x plus 4x squared, all multiplied by x. Multiply that x through and simplify, we end up with 4x minus 8x squared plus 4x cubed. And as we can see, we rewrite that to 4x cubed plus 4x minus, let's rewrite it in the form that we're used to, minus 8x squared plus 4x, which is exactly what we needed there. Okay. On to part B. Find the value of x that gives the box its maximum volume and show the volume is a maximum. So we want to find the maximum volume. So to do that, we've got to differentiate this. So I'm going to say that dv dx equals 12x squared minus 8x plus 4. We want to find the maximum volume, so we want to find a turning point. What do we have to do with her derivative? Let it equal 0. So that means that we've got 12x squared minus 8x plus 4 equals 0. I'm going to divide everything by 4. So we've got 3x squared minus 2x. I've made a mistake. Okay, I found it. Alright, we've got that thing there, so dv dx equals 12x cubed minus 16x, and it should be squared. Making too many mistakes. 12x squared minus 16x plus 4. Now, to find a maximum, I've got to let my derivative equal 0. So 12x squared minus 16x plus 4 equals 0. Luckily, all those can be divided by 4, and I end up with 3x squared minus 4x plus 1 equals 0. So from there, that tells me that I'm going to have I'll factorise that to 3x minus 1 and x minus 1. So that tells me that x equals 1 over 3 and x equals 1. So one of these two will give me a maximum volume. If we substitute x equals a third into here, we'll end up with a distance here. If we substitute x equals 1, given that we've got 2 meters here, it's not going to work. We're not going to get a volume. If we substitute 1 into here, we'll get 4 minus 8 to give us negative 4, plus 4 will give us 0. So we can ignore this. Our maximum occurs here at x equals a third. So when x is a third, we'll have a maximum there. Now we want to show that it's a maximum. Well, what we do, we set up a table. So what we'll do, we'll pick some values, and we'll say we are going to, when x equals 0, when x equals a third, when x equals a half, when x equals 1, and when x equals 2. So we know that at a third is 0, and at 1 it's 0. So working out the rest of them. So if we substitute 0 into the derivative, we end up with 4, which is positive. We substitute a half, we get negative 1, which is negative. And if we substitute 2, we get, substitute 2 into the derivative, we end up with 16, which is also positive. So it tells us we've got positive, 0, negative, 0, positive. So hence, at a third, it is at a maximum. Second last thing they ask you to do is to sketch a graph over a suitable domain. So what we end up with here is we have a graph where it's going to cut through at 0, and then it's going to bounce there and bounce off there. So here we're at 1, and over here we're at 1 over 3. Now, so let's do it over a suitable domain. Given that we're dealing with a real life thing, we can't have any x values which are negative. We also can't have any x values which are greater than 1, because if that happens, then we don't have a box. As soon as we cut out anything that's less than a negative number, we're in fact adding things onto the box. And if we cut off more than 1, well then we're cutting off more than half. And as a result, we're not going to have a box. So, based on that, I'm going to change the domain between 0 and 1. And I'm going to have the turning point here at 1 over 3. Now, the last question tells us if the height of the box must be less than 0.3, so x has to be less than or equal to 0.3, what's the maximum value of the box? Now, looking at it, I know that 0.3 is less than a third. I know it's somewhere around here. So to find out the maximum volume of the box, what I do is I take my original equation of 4x cubed minus 8x squared plus 4x, and I substitute x equals 0.3. So that'd be 0.3 cubed minus 8, 0.3 squared plus 4, 0.3. And then on my trusty CAS, I substitute that value of x, I evaluated that, and I find out what my maximum volume is.